Chapter 6 in your textbook is entitled The Electronic Structure of Atoms. We understand that atoms are made up of protons, neutrons, and electrons. Well, the protons and the neutrons contribute appreciably to the mass of an atom. The electronic structure is what gives an atom its reactivity or lack of reactivity. So in order to understand the nature of chemical interactions, we're going to need to understand the electronic structure of atoms. Now, when we refer to the electronic structure, what we're actually talking about, the arrangement spatially of electrons with respect to the nucleus and with respect to each other, as well as the energy of these electrons. In our initial conversation, we're going to find ourselves talking about waves. And I know that that seems like an out of the ordinary way to start talking about matter, particles, but trust me, in order to fully understand how these small particles behave, the understanding of wave-like behavior must be fundamental. In order to understand the electronic structure of atoms, we must gain an understanding of the concept of electromagnetic radiation, otherwise known as light. Now, electromagnetic radiation propagates as waves traveling through space at the speed of light. Now, a wave is nothing more than a periodic disturbance, but a wave can be characterized in a number of ways. In the same way that matter possesses mass and position or location, waves have fundamental properties that can be used to describe them, one of which is the wavelength. If we do find a periodic disturbance that is repeating, the wavelength is the distance between corresponding points on adjacent cycles of a wave. It is indicated by the Greek letter lambda. Another property of waves is the frequency. The term frequency refers to the number of cycles of a wave that pass a given point during a given amount of time. It should be noted that if these two waves, A and B, are propagating at the same speed or the same velocity, we'll note that one of them has a longer wavelength, that would be A, but B would have the larger frequency. So the relationship between frequency and wavelength is an inverse relationship. As the frequency gets smaller, the wavelength would get larger. Here we see an image reflecting the electromagnetic spectrum. On one end of the spectrum, we see things like gamma rays and X-rays. On the other end of the spectrum, we see radio frequency waves. Now, while this entire spectrum represents electromagnetic radiation, understand that each type of electromagnetic radiation can be characterized by different wavelengths and different frequencies. Since they all travel at the same velocity, the speed of light, which is 300 million meters per second. When going from one type of radiation to another, remember the idea. If we see an increase in wavelength, then we would see a subsequent decrease in frequency. Here we see some common wavelength units for different types of electromagnetic radiation. X-rays, which have a very small wavelength, are typically measured in units of angstroms, a measurement which is on the order of 10 to the minus 10th meters. Radio waves can be measured in units of meters or even kilometers. The visible portion of the spectrum resides in the nanometer range. A nanometer is 1/billionth of a meter. So approximately between 400 nanometers and 800 nanometers is the portion of the electromagnetic spectrum that we can see with the naked eye. In order to understand different phenomena, we have to look outside the box. For example, when an object increases in temperature, you can oftentimes see it glowing red hot, orange, or even white hot. Now that's because of the absorption of energy. But the wave-like nature of energy doesn't explain this particular phenomenon. An explanation was put forward by a German scientist by the name of Max Planck, and he theorized that energy had to exist in concrete, discrete amounts, packets of energy known as quanta. So in order to achieve a change, energy had to be absorbed in these particular amounts. The original thought with regards to energy is that any amount of energy could be used in order to excite matter to a higher state of energy. But it turns out that if, as Planck theorized, energy is indeed quantized, then there are certain levels that cannot be reached. For example, I would like for you to imagine walking up a flight of stairs. If each stair is 1 foot tall, then you can achieve a height from the bottom of 3 feet by walking up 3 stairs. But you cannot achieve a final height of 2.5 feet. You can only travel up the stairs in certain increments. And that is what Planck suggested with respect to energy. Energy could be used to excite motion, but only in specific and discrete amounts. Albert Einstein used the idea of quanta, or these quantized packets of energy, to explain the photoelectric effect. This is the work for which Einstein received the Nobel Prize. Upon irradiating a metal with light, electrons can be emitted. But a few things have to be taken into consideration. Each metal has a different energy at which it will eject electrons. If the energy that impinges on the metal is not energetic enough, then we will not see electrons emitted. So with that being said, once again, the idea of the quantization of energy must hold true. Einstein concluded that energy was directly proportional to frequency, with the relationship E is equal to h times nu, where the energy is equal to Planck's constant times the frequency. Well, if waves can behave like matter, then why can matter not behave like waves? A French scientist by the name of Louis de Broglie theorized that if light can indeed possess properties of matter, then matter should be able to do the same. And he suggested the relationship between the mass of a substance and its wavelength by the formula listed below. The concept of the wave-like nature of matter is very important in areas such as diffraction and quantum mechanics in general. Matter can only exhibit wave-like properties when the matter itself is extremely small. For example, as a person, I have a frequency, I have a wavelength, but it is not detectable or meaningful because my mass is, let's just say, a little too large. In order for us to speak of the wave-like properties of matter, the particles themselves have to be small enough that their wave-like properties would be observable on the order of the length of electromagnetic radiation. And so scientists like Werner Heisenberg attempted to explain the behavior of an electron. The problem is an electron is a really, really, really small particle that has position slash location, but it's moving really, really, really fast. In instances upwards of 100,000 meters per second. Think about that as being on the order of 60 miles per second. So imagine trying to find a tiny little particle that's traveling at 60 miles per second in a small volume of space. Heisenberg put forth what we know as the Heisenberg uncertainty principle, which says that it is impossible to simultaneously determine the position of a particle as well as its momentum or the energy associated with it. And if we stopped there, we would pack up our things and go home, never having an explanation or an understanding of how an electron behaves within an atom. But that was not the end of the story. Pioneers such as Erwin Schrödinger went forth and developed a mathematical equation which would allow us to treat a particle like an electron as a wave. In doing so, we would be able to gain some understanding as to how it is moving and where it is likely to be found. Now, unlike most simple equations, x plus 3 equals 5, for example, the solution to x plus 3 equals 5 is that x is equal to 2. Schrodinger's equation, on the other hand, has many, 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 many solutions. And all of these solutions collectively can be treated in such a fashion that they will yield a probability or a likelihood of finding an electron in a particular volume of space. So we've taken a mathematical construct and used it to speak to a spatial property. All of these solutions to the Schrodinger equation for a given electron combine to form what we call an orbital. The term orbital spatially refers to a volume in three-dimensional space where the likelihood of finding an electron is high. Each orbital describes a particular area in space where the electron might be found. For our discussion today, we're going to speak of four basic types of orbitals. There are s orbitals, p orbitals, d orbitals, and f orbitals. You'll note the difference in the orbitals in terms of the shape or the solutions to the Schrodinger equation that give rise to different spatial orientations about the nucleus. Noting the difference between the spherical s orbital and the lobe-shaped p orbitals, we see that p orbitals have two lobes of electron density along three different axes, the x, the y, and the z-axis. In one instance, we find solutions that would suggest that electrons can be found above and beneath the nucleus, but not in the other two axes. So these three axes collectively speak to p orbital electron distribution for a particular energy level. D orbitals have a different spatial orientation altogether. While we typically see these lobes that we are familiar with respect to p orbitals. D orbitals have 4 lobes, at least most of them do. In any given energy level, we find 5 different d orbitals. 4 of them have electron density that exists in a particular plane, while the 5th one resembles a p orbital with electron density above and beneath, while there's an additional donut-shaped ring of electron density around the center. And as far as f orbitals are concerned, well, their shapes are complicated. Many of them have 8 lobes of electron density. It's important to note that whenever we find f orbitals in a particular energy level, that there are 7 f orbitals per energy level. Now, there are a few things to take note of with regards to these electron orbitals. As the number of electrons increases in an atom, so does the repulsion between them. Electrons are negatively charged. Electrons don't want to have anything to do with each other. They tend to repel one another. Positive attracts negative, negative repels negative. So in atoms where we see more than one electron, not all of the orbitals in the same energy level are degenerate. Now, the term degenerate refers to having the same energy. Orbitals that are of the same sublevel are indeed degenerate, but s orbitals in the 3rd energy level do not have the same energy as p orbitals in the 3rd energy level. And as we start to build up what we ultimately will call an energy level diagram, we're going to see that the energy levels start to overlap in energy, making things a little complicated initially to understand, but with a few things taken into consideration and a tool or two at our disposal, then we should be able to predict the order of orbitals going from lowest to highest. Here are a few things that we need to take into consideration. As we get farther and farther away from the nucleus, we can think about regions in space where electrons are likely to be found. Electrons that are closest to the nucleus are said to be in lower energy levels. As we get farther and farther away, we would say that the electrons are in higher energy levels, suggesting that the energy of an electron is related to the distance from the nucleus. Now, if we speak of energy levels in a quantifiable manner, N references the energy level in question. N equals 1 is the closest energy level to the nucleus. N equals 2 is slightly farther away. N equals 3, N equals 4, ad infinitum. Well, in each energy level, we find a different set of orbitals. In the first energy level, we only find one type of orbital, and that is the s orbital. In the second energy level, we find s's and p orbitals. In the third energy level, we find 3 types, s's and p's and d's. And in the fourth energy level and beyond, that means the 4th, the 5th, the 6th, the 7th, then we find 4 types of orbitals, the s, the p, the d, and the f. Now, when we do experience s orbitals, when we observe s orbitals, when s orbitals are present in an energy level, there's only one s orbital per energy level. Whenever we find p orbitals in an energy level, there are 3 p orbitals per energy level. Whenever we encounter d's, there are 5 per energy level. And if there is an energy level that possesses f orbitals, there are 7 f orbitals. The last thing to take note of, in a particular energy level, electrons that reside in s orbitals are of lower energy than those in p orbitals, which are of lower energy than those in d orbitals, which are of lower energy than those in f orbitals. So if we take into consideration the fourth energy level, where we have 4s orbitals and 4p orbitals and 4d orbitals and 4f orbitals, if we have electrons residing in all of those orbitals, the electrons in the 4s are going to be of lesser energy than the rest. So those will most likely be found closer to the nucleus. Those in the 4f, being of the greatest energy, will be found the farthest away from the nucleus. So here I have exhibited the various energy levels, the S, the P, the D, and the F, for the first 6 energy levels. You will note that in the case of the first energy level, we find a single s orbital. In the case of the second energy level, we find a single 2s and 3 2p orbitals. In the third energy level, we find s's and p's and d's, all of the appropriate number. And for the fourth energy level, the fifth energy level, and the sixth energy level, we see all 4 types of orbitals. Now, what I have done here is I have staggered them from left to right to kind of give you an idea as to how these things exist. But if we truly want to understand how these orbitals stack, then we have to look from lowest energy to highest energy. In other words, we need to try to squish this together so that instead of staggering it from left to right, we truly see what is the lowest and what is the highest energy orbital. Now, when we begin this, I don't think we're going to have any problems. I think that we can just eyeball it and see that the 1s is the lowest of all of the orbitals listed on the screen currently. And the 6f is the highest one listed. But if we were to go in order of lowest to highest energy, please understand that there is significant overlap. If we were to squish these together, we see that above the 3p, before we get to the 3d, we find that the 4s is lower on the screen, which suggests that it is of a lower energy. We similarly see overlap between the fourth energy level and the fifth energy level, and between the fifth energy level and the sixth energy level. So if I were to ask you which orbitals were of the lowest energy, which were of the highest energy, and can you order all of these orbitals from lowest to highest energy correctly? Would you be able to do it? Well, let's give it a shot. And in order to do so, I'm going to stack them atop one another. First, we see the first energy level, all by itself, the single 1s orbital that exists in the first energy level. Now we're going to add the second energy level, followed by the third energy level, and the fourth energy level, where we start to see that overlap. Now, it may be hard to see, but slightly above the 3p set of orbitals, we find the 4s before we get to the 3d. And just when you thought that that was the end of the overlap, we see that in the fifth energy level, we see even more overlap. The 5s being of lower energy than the 4d, the 5p being of lower energy than the 4f. Well, I'd really hate to see what adding the sixth energy level does with regards to this ordered structure. Yeah, that's kind of what I thought was going to happen. It seems that it has introduced a tiny bit of uncertainty. When we take a look at these orbitals, now, if I were to ask you to order them from lowest to highest, then you might say that the 1s is the lowest, followed by the 2s, followed by the 2p, followed by the 3s, followed by the 3p, followed by the 4s because of the overlap, followed by the 3d, followed by the 4p, followed by the 5s, followed by the 4d, followed by the 5p, and then the 6s and the 4f are really close, but it looks like the 6s is a little bit lower. And then above the 4f, we find the 5p D or the 6p? Once again, the overlap is so hard for me to tell. Then it would be unreasonable for me to ask you to be able to detect it simply using your eye. Well, thankfully, there's a tool that we can use that will help us to reproduce the order of these orbitals from lowest to highest energy. And it also includes the 7th energy level and the 8th energy level as well. The structure that you see before you currently shows the first energy level and its s orbital, the second energy level and the s and p orbital, the third energy level, the sp and d orbitals, and then the 4th through 8th energy levels with s, p, d, and f orbitals represented respectively. Now the question is, how can we use this in order to predict the order of the orbitals? Now, we're not going to simply read them from left to right. If we read them from left to right, then we would show no overlap, and we know that overlap does exist between these orbitals. Instead, upon reproducing this image, we can use a series of arrows that will travel from one box through the structure until we reach a point where we can determine the lowest to highest energy orbitals. Well, here we go. We now see a series of lines that are drawn through each box. As we go across the top, we encounter the first arrow that goes through the 1s. And then the next arrow, as we travel from the tail of the arrow to the tip of the arrow, goes through the 2s. The next arrow goes through the 2p, followed by the 3s. The next arrow goes through the 3p, followed by the 4s, which is where we start to see this overlap take place. The next arrow goes through the 3d, followed by the 4p, followed by the 5s. The next arrow goes through the 4d, followed by the 5p, followed by the 6s. The next arrow goes to the 4f, the 5d, the 6p, the 7s. And the next arrow goes through the 5f, the 6d, the 7p, and the 8s. If we continue this, then we would be able to build a structure from lowest to highest energy, because as each arrow passes through one of these orbitals, if we read this from tail to tip of each arrow, we can stack this from lowest to highest energy, and it will reproduce what we know to be true in terms of the ordering of the orbitals. Now, there are a few basic principles and rules they're going to use in order to account for electrons as they reside in these orbitals. The first of which is the Aufbau principle. The Aufbau principle suggests that electrons can be found in the lowest possible energy levels. When accounting for electrons in an atom, electrons tend to fill the orbitals of the lowest energy before occupying higher energy level orbitals. So if we were looking at the 2 electrons in an atom of helium, we would not likely look for them in the 3d set of orbitals, since there are significantly more energy levels of lower energy than that. Since the lowest possible energy level is the 1s, that might be a good place to start looking for those electrons. Now, the word Aufbau is a German word that means building up. And so as we start to construct these energy level diagrams, we're going to see that we add electrons from the bottom up. Another principle at play when speaking of the electron orientation in an atom is the Pauli exclusion principle, named after Wolfgang Pauli. It suggests that no 2 electrons in the same atom can have the same energy. Specifically, it says that no 2 electrons may possess the same set of 4 quantum numbers. The term quantum numbers refers to some descriptors for electrons that speak to the spatial orientation and the spin that these electrons possess. When we speak of the orientation of electrons within an atom, we typically refer to it as the electron configuration. And it's often expressed in what we call SPDF notation. The most stable organization, the most stable orientation is the lowest energy state, which we refer to as the ground state. And when referring to the SPDF notation, it's going to read from left to right almost like a sentence, but without words. And trust me, that'll make sense in just a moment. Each component of SPDF notation consists of a number referring to the energy level, a letter speaking to the type of orbital in that energy level, and a superscript which speaks to the number of electrons that can be found in that particular orbital. An orbital diagram is going to be a graphical representation as to the ordering of the electrons from lowest to highest energy. We typically use half arrows, or arrows pointing up and arrows pointing down, to indicate the electrons. In a particular orbital, we can have no more than 2 electrons. So an orbital can have no electrons, 1 electron, or 2 electrons. This is reflected in the Pauli exclusion principle by saying that these electrons cannot have the same energies. While 2 electrons may exist in the same orbital, if they do, they must be of opposite spin. The direction of the arrow represents the relative spin. So it would be inappropriate, it would be improper, it would be incorrect to place 2 electrons in the same orbital of the same spin. That essentially means that the electron is found in the same energy level, in the same type of orbital, in the same specific orbital, and is of the same spin orientation. And those 4 things are the 4 quantum numbers that we spoke of previously in short. So if an electron is found in the same energy level, in the same type of orbital, in the same orbital specifically as another electron, then it must be of opposite spin so as not to violate the Pauli exclusion principle. Now what we see here is a lithium atom in which we see 3 electrons. Well, if electrons can be found in the lowest possible energy orbital, then we would see that first we would account for electrons in the 1s. Now for our purposes, let's start by drawing an arrow pointed up. The first electron entering into an orbital, we're going to account for it as being spin up. The second electron accounted for is going to be found in that same orbital, but spin down. The third electron is going to be found in the next highest orbital, spin up. We can't place all 3 of them in an orbital. That again would be a violation of the Pauli exclusion principle. Now, as we add more and more electrons, we're going to find ourselves wondering exactly where do we place them, specifically when we encounter degenerate orbitals or orbitals of equal energy. When we find multiple orbitals of a particular type, for example, the 2p orbitals that we find, or the 3d orbitals, or the 4f orbitals, Each of these sets of orbitals are degenerate with one another. So all of the 4f orbitals are of the same energy. So when we're accounting for the electrons, when we're placing 3 electrons into an atom of lithium, or rather accounting for the 3 electrons by placing them into an energy level diagram, then we're going to see 2 of them in the 1s, 1 of them in the 2s. With beryllium, we're going to add an additional electron, and since it's going to obey the Aufbau principle, going from the lowest to the highest, that electron will be in the 2s. The 5th electron, when we account for the 5 electrons in an atom of boron, then we see 2 found in the 1s, 2 found in the 2s, 1 in the 2p. As we approach carbon, we find ourselves with a bit of a question. Do we place that 6th electron in the same p orbital as the electron that we found in boron? Do electrons tend to pair up, or do they tend to space themselves out? Well, once again, remember, electrons don't want to pair up. Electrons don't particularly care for one another. Electrons are negatively charged. The only reason why we do find them in the same orbital is because that represents a lower energy orbital, and electrons are always in the ground state going to be found in the lowest possible energy orbital, even if it means that they have to pair up. But if they don't have to pair up, if they can enter into an orbital of equal energy without pairing up, then they're going to do so. This is an example of Hund's rule, which says that when filling degenerate orbitals, the lowest energy is attained when the number of electrons having the same spin is maximized. So rather than pairing up, electrons will enter into empty orbitals of equal energy. That's a lot of E's. Now, with those rules in mind, we can build an energy level diagram that will encompass all 118 electrons in an atom of organosun, or the 1 electron in an atom of hydrogen, and all points in between. Elements in the same group, the same vertical column, tend to have the same number of electrons in the outermost shell. Now, these electrons we refer to as valence electrons, and they're important because valence electrons are instrumental in chemical bonding. Valence electrons are defined as those electrons found in the highest numerical energy level in both the s and p orbitals. Electrons that are found in inner shells are referred to as core electrons. These would refer to d orbitals, f orbitals, and s and p orbitals of lower numerical energy levels. And we can use a noble gas abbreviated SPDF notation to speak to the electron configuration of larger and larger atoms. For example, I don't think that we would want to include all of the orbitals in an atom of organosun if we were trying to succinctly describe its electron configuration. I don't think that we would want to use all of the orbitals in an atom of copper, even though copper only has 29 electrons. It's still a significant number of orbitals to refer to. If we refer back to the previous noble gas and simply list the orbitals that exist in the valence level, or since the previous noble gas, that is reflected in what we call noble gas abbreviated SPDF notation. The image at the bottom of your screen is an illustration of the elements on the periodic table with respect to the last electrons accounted for when going from lowest to highest energy. For example, the blue block of elements fall in what we call the S block, where the last electron accounted for is going to be in an s orbital of the corresponding energy level listed. The pink block that we find on the right-hand side is known as the p block, where we see p electrons are the last ones accounted for from lowest to highest energy. For example, if you find carbon on your periodic table, you're going to find it in the p block, specifically in the period labeled as 2p. So when we account for the 6 electrons in carbon, we're going to see the 2p is where the last electrons can be found. The orange block is known as the D block. It's where we find those transition metals. And the F block, which typically we find as the disjointed area at the bottom of the periodic table. That's where we find the lanthanoids and the actinoids. The F electrons are found there. And just as a final reminder, the transition metals are where we start to see this overlap between the orbitals take place. If we account for element number 18, argon, it would have an SPDF notation read as 1s2, 2s2, 2p6, 3s2, 3p6. Since we know the orbital overlap suggests the next electron would be found in an s orbital, specifically the 4s orbital. Potassium at element number 19 would have that same electron configuration, but with an added 4s1. Calcium would have the same electron configuration of argon plus 2 electrons in the 4s. So it would read 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now the transition metals are where we see that overlap coming back into place, where we see the 3D filling. So scandium, element number 21, would look just like argon, the previous noble gas, with an added 4s2 and an additional 3d1. The disjointed area that we find at the bottom of the periodic table includes two periods known as the lanthanoids and the actinoids. The lanthanoids, which are similar to lanthanum, and the actinoids, which are similar to actinium, all have electrons that are entering into f orbitals. These periods have more in common with each other than in any particular group. Typically, we think of elements in the same group of having similar properties. Well, in these two disjointed areas, we find that the lanthanoids have more to do with one another than stacking in a particular group. So lanthanum has more in common with samarium and promethium than it does with other elements. In the actinoids, we see things like uranium, plutonium, neptunium, californium, americium. They tend to have similar properties, and that we see that electrons are entering into the 5f sublevel in the actinoids, while they are entering into the 4f in the lanthanoids. And for the most part, the periodic table goes nice and neat with regards to electron configuration, obeying the Aufbau principle. Now, I wouldn't have said most if I meant to say all. There are, of course, going to be some exceptions to the rule. And while the exceptions are noteworthy. They're not going to affect our general understanding of the organization and electron configuration, respectively. Now, the two purple arrows are set to indicate different anomalies, behavior that does not follow the Aufbau principle. Now, the arrows aren't meant to suggest that the entire vertical column, the entire group, including copper, silver, gold, ruthenium, and chromium, molybdenum, tungsten, and seaborgium, it's not to suggest that all of them behave errantly. But specifically, I want to point to chromium and copper, elements 24 and 29. These represent departures from the Aufbau principle. Typically, we would expect the ordering to go from lowest to highest, Hund's rule to be obeyed, as well as the Pauli exclusion principle to come into play. So how do these two elements, chromium and copper, represent departures or exceptions to the Aufbau principle? Well, if we were filling chromium as we would suspect, then we would fill up the 1s, the 2s, the 2p, the 3s, and the 3p, as would be the case in an atom of argon, followed by the 4s2, and then placing 4 electrons in the 3d. It turns out that instead, in actuality, chromium has an electron configuration that looks like that of argon plus a 4s1 and a 3d5. So why is it that the 4s isn't filled and we see the filling of the 3d? Well, this is because the 3d and the 4s are very, very close in energy. And it turns out that a half-filled set of d orbitals or a half-filled set of f orbitals suggests or confers a certain sense of electronic stability. So by having 5 electrons out of a possible 10 in the d orbitals, that speaks to a certain level of stability. So 1 electron is elevated from the 4s to the 3d in order to stabilize it in this particular fashion. Now, with the next atom, manganese, we would see the filling of the 4s, bringing it to a 4s2, 3d5. And then we would continue adding electrons in the 3d until we get to copper, where we would see a similar phenomenon. Copper has an SPDF notation of looking like argon plus a 4s1 and a 3d10. Once again, we see a benefit electronically from having a completely filled set of d orbitals or f orbitals, even if it means pulling one from the 4s, which again is very near the 3d in energy. Thank you for your time. Thank you for listening. Here's hoping that you learned a little something. Talk to you soon.